Hey guys, this is Professor Janacek. Want to talk about power series. Want to go over another example of a Taylor series. Recall that a Taylor series for f of x about x equal to a has the form of f of x equal to the sum as k goes from 0 to infinity of the kth derivative of f evaluated at a over k factorial times the quantity of x minus a raised to the k. So let's take a look at a Taylor series for the cosine of x about pi. So our function in this case, f of x, is the cosine of x. First thing we need to do is see if we can come up with pattern for that kth derivative there in the numerator. So the first derivative of cosine would be negative sine of x. The second derivative of f would be, what is that, negative cosine of x. Third derivative gives us positive sine of x. The fourth derivative, we now get cosine of x, and you can see now we've got our pattern. We're going to just start repeating this. Write out one more, but hopefully everyone sees what that looks like. All right, so now we need to evaluate this at our a value. This is going to be centered around pi, so let's evaluate all of these at pi. F at pi, cosine of pi, that's simply negative 1. The first derivative at pi, negative sine of pi, well, that's 0. Second derivative at pi, that's negative of a negative 1, which would be positive 1. Third derivative, evaluated at pi, gives us 0 again. The fourth derivative, evaluated at pi, gives us negative 1 again. Fifth derivative, of course, is going to give us 0 one more time. And again, I think that's probably enough so that we can kind of see the pattern of what's going on here. Negative 1, 0, positive 1, 0, negative 1, 0. Let's see if we can build our Taylor series now. So our function is cosine of x. Just looking again here at the top of the page to kind of build out that series, it's going to be the sum as k goes from 0 to infinity of the kth derivative evaluated at pi over k factorial times x minus pi raised to the k. All right, that's what it looks like. I think in this case it might be really useful to kind of look at some of the terms. So let's go through, and if we evaluate this at 0, we have the 0th derivative evaluated at pi over 0 factorial. And then the exponent there in the back is 0. When k is equal to 1, we have the first derivative over 1 factorial, x minus pi to the 1. When k is 2, we have the second derivative over 2 factorial, x minus pi squared. K is equal to 3, it's the third derivative over 3 factorial. And I'm just doing one little bit here at a time just so we can start to kind of fill it all in without too much difficulty. When k is 4, we have the fourth derivative over 4 factorial, x minus pi to the 4th. The fifth derivative, I'm not going to write down. You can write that one down. I'm running out of room here. And I also recognize it's going to be equal to 0. All right, so let's see. Let's go ahead and put those numbers in. Again, I'm going to look at these values that I have here and just fill in those on each term. F at 0 is negative 1 over 0 factorial. F prime gave us 0. Again, that's all I'm doing in this case, in this step. I don't want to get ahead of myself. I don't want to lose anyone. The second derivative at pi gave us a positive 1. Third derivative, we got 0 again. Fourth derivative gave us -1 there in the numerator. And of course, again, if you had written out the fifth term, you would see that that would be a 0 as well. All right, I think I can simplify this a bit. I noticed that a 0 in the numerator here means that that whole term is going to go away. Same thing with this term. That would also be the case for k equal to fifth 5, that last term there, if I had written it down. So let's go ahead and rewrite that without those terms. And again, I'm just going to get rid of those 0 terms so I don't have to worry about those anymore. And I think that's about as simplified as we can get on this. Let's see if we can write this as a summation now. We have, let's start with f of x equal to the cosine of x. Now the way I'm going to do this, I'm going to imagine that, okay, this is when k is equal to 0, this is when k is equal to 1, this is when k is equal to 2, etc. So we have, first off, it's the sum as k goes from 0 to infinity. I notice that we have alternating sign, -1, +1, -1, so on and so forth. Well, how do we get alternating signs? Well, that's -1 raised to a power. I want this to be an alternating sign starting with a negative, so I'm going to write it, and notice also that my k is starting at 0. You can try a few if you need, but that k plus 1 should do the trick for us. There are a few other options, but I think k plus 1 there in the exponent is the easiest. In the denominator, I have 0 factorial when k is 0, 2 factorial when k is 1, and we have 4, oh, that's supposed to be a factorial on there, when k is 2. So looking at that pattern, I see that it should be easy to understand if I have just 2k factorial. In the denominator, those look like even numbers, 0, 2, 4, so I'll write it as 2k. Of course, they're factorial, so it's 2k factorial. Then we have this multiplied by x minus pi raised to, I notice that the denominator is the same, or the value in the denominator is the same in the exponent. So whatever I'm taking a factorial of in the denominator, that's what I'm going to use as my exponent, which we just wrote as 2k. And there we go. Now, isn't this amazing? We have the cosine, a transcendental function, is written as, this whole thing here, a polynomial. Albeit an infinite polynomial, it's still a polynomial. Calculators often use this when doing computations for their trigonometric functions. They are not programmed with values. They don't use unit circles. They actually use this Taylor series, very common. Hope you enjoy.